So last time we were talking about analog position and velocity sensors. We talked about potentiometers and LVDT and Hall effect sensors, and then we also talked about tachometers for velocity. And remember, one of the problems with a tachometer was that because it's an analog system, there's noise on it, and we don't necessarily know when the tach is reading zero speed or whether it's reading noise or a slow speed. So one of the ways we can get around that is by using a digital sensor. And so we want to talk about different schemes for digital velocity and position measurement. And I say velocity and position because we're going to start with velocity and then go to position. So consider first a block that's moving at a fixed velocity. And so we've got these switches. I've got 3 of them drawn in here. And as the block moves past, it's going to depress this switch, and so the switch is going to trigger a high voltage as long as the block is depressing it. And so when the block has moved just past the switch, you would expect it to drop low again. And then we'll move past the second one, and that one will go high, and we'll move past the third one, and that one will go high. And so you can see that as we move across here, we expect to get an output voltage that looks like this, where there is a high voltage for the duration of the block sliding across that switch, and low voltages elsewhere. And so we get these pulses, and we want to look at how to relate these pulses, which are digital, on or off, into the speed or the position of the block. And so you can see right away that the velocity here is encoded either by the frequency of those pulses or the period of the pulses. Either way, we can go at it, and it'll give us velocity. Now, you can also see that if the block were to move forwards a little bit, and then backwards a little bit, and forwards a little bit some more, then it's between the switches, and we don't see anything. So there are problems, and we will have to design our density of our switches very, very appropriately. But certainly this will work as long as we do things right. So how do we generate those pulses? I mentioned mechanical switches just because that's the first thing that I think of as being sort of intuitive. But what other types of switches might you see? Well, you might see magnetic, which we were looking at Hall effect sensors, and when we looked at Hall effect sensors, we mentioned that we could have a toothed gear or something going around that the Hall effect sensor is going to periodically see one of those teeth and register it as a pulse. So that's one option. We could do the same sort of thing with a visual system, an optical system, where we are looking between those teeth or hitting a teeth. We could do reluctance. That's not how you spell reluctance. There we go. We might also do something like pressure. If you think about driving along on the road, sometimes you see those little black hoses across the road. Essentially, you're triggering them with a pulse because you're driving over them. It's going to cause a pressure to be registered. In any case, we're going to generate these pulses, and they should be reasonably clean. That's to say, nice and digital 0 and 1, so we might have to clean them up with a Schmidt trigger or the like. But in any case, we're generating pulses, and we're looking at how our thingamajig is moving relative to these pulses. And so I mentioned we could do frequency or period. So if we do frequency, one thing we can do is we can use a frequency to voltage converter. It's an IC like a LM2917 or an AD650, and it's going to generate an analog voltage that's going to be proportional to frequency. And so we could read that in through an ADC, which, you know, now we've gone back to analog, so we've got noise again, but still it's a possibility. It may not be the best possibility, but it is a possibility. We could also come up with a timed voltage converter where we are counting a number of clock cycles between the first pulse and the next pulse, and maybe we just let the clock run and we'll just count them up and then start the counter over again. So these are options. One of the options that we're going to look at, though, is called pulse frequency modulation. So we're going to go back to that frequency, and instead of going through the ADC, because why would we go back to analog? Instead, what we're going to do is we're going to count the number of pulses within a fixed time. So I mentioned you can go to a frequency to voltage converter, or you can count the time between pulses. Well, let's count the pulses within a time. And since we know that we're going to velocity, which is proportional to the frequency, we can say that our velocity, proportional to our frequency of pulses, would just be the number of pulses in some fixed time. And so if we count all those and we know what the time is, then by that we ought to have our pulse frequency. So how would we do that? Well, why don't we do it as a state machine? We like state machines. And so if we start there from the start position, we move into that first state, and these are, you notice that these are not going to be purely digital input and output states, and they don't even have all the transitions labeled, but it's roughly the idea of a state machine. You could clean it up if you like. So we'll start by clearing our output latch, because we want to start with all of the garbage gone in there. And so we'll reset our counter, we'll set our timer, we'll start the timer, and we'll just sit there and run until the timer's finished. And when the timer's done, we'll read the output. How many counts do we have? And so as you're looking at this, I'm hoping that you're looking at this and you're saying, I don't like that. But why don't you like that? What are the errors that could occur in this system? I'll let you think about that. What are the potential errors that could occur in this very simple state machine? Well, what happens if you have too many counts? I mean, you have to allocate some amount of memory for your output latch, or your counter rather. If you don't allocate enough memory for your counter and you've got too many counts, what's happened? Well, you've got overflow. That's not good. What happens if you have too few counts? You've got, 1,000 seconds, but you only have one count. Your resolution is terrible. So if we have too many or too few counts, that's not good. We might also have some latency in the system that could be causing problems. So we want to try to fix this. And the first thing we'll fix is the overflow, because that's an easy one. So let's modify this and add a counter overflow condition. So we'll do the same sort of thing. We'll start by clearing the output latch, we'll reset the counter, we'll set the timer, we'll start the timer, and then we'll run. And now, if the overflow is triggered, then we will set our output latch to the maximum and start over. Or, if the timer's done and we've not overflowed, then we'll read the counter and start over. But in this case, now, we are avoiding our overflow problem. Now, you'll still have to come up with a nice way to address the low count problem, and that may be as simple as just when you hit the end of the timer, if you don't have sufficient counts, maybe you just don't use that value. I'm sure you could come up with other ways to do it, though. So another thing you could do is you could use handshaking, which is to say when you've got your two systems and they're talking to each other, you could have one system ask the other if the data's ready. That way you make sure that you don't read at a bad time. Remember, we talked about gray code as a way to deal with asynchronous inputs, so that we would always be reading things that were correct. Well, handshaking is another option. You verify that the output latch information, the data, is only going to be read when it's correct, and you can do that by having another output that's going to say, is the data ready or is it not ready? You could do this in software, but I would tell you that your timer should not be done in software. You should use something like a 555 timer. And you could certainly do like a timer interrupt, and we'll talk about timer interrupts a bit in 6183, or you can read about them now if you'd like. But timer interrupts are a nice way to tell your micro that it's time to do something. You could so that would be using the micro for the timer. You could use it as a hardware interrupt with a 555 timer. Either way, and still you're going to run into processor speed limitations, because if you've got other things going on and you've got this timer and this counting going on, then maybe you're going to be running out of processing power. And if you're running out of processing power, maybe you use like a ripple counter instead. A ripple counter being a hardware IC that's going to do your counting for you. And that way you just read it, you let the ripple counter go, you use a electronic system essentially, and periodically you pull it with your micro. So those are different options. You have to look at what's appropriate for your particular system, whether you want to do it all in software, whether you want to do it in hardware, whether you want to mix it up. But make sure that you know what your limitations are. So what affects the precision? Well, if you think about it, if it's moving very quickly, and I mentioned this, you get lots of pulses, and that's when you run into the potential overflow case. And so with lots of pulses, you've got relatively high precision, because remember that your velocity is going to be your number of pulses divided by your time, and I'm going to go ahead and say plus or minus some delta because there's potentially some error in your time measurement. And so if you've got a lot of pulses, you can detect a relatively small change in velocity. But if you've got very few pulses, again, if you've got 100 seconds but you've only got 2 pulses, then you are dealing with low precision. And so we'd like a way around this. We'd like to be able to come up with a way to deal with our low speed cases as well. Our high speed cases, this works fine. We can increase the timing period, certainly increase your delta t, and so that'll help us with our precision. But again, that's a memory problem. It's a we got to worry about what the sampling availability is of our system. We could also use just a different pulse generating device. So if you're using mechanical switches, why don't we add more mechanical switches? If you're using optical, if you're using like an optical disc or something that's got alternating transparent and opaque sections, why don't we just go ahead and make them denser? And that way we'll get more counts. So that'll help. But we do have to still worry about things like the accuracy of the timing. I mentioned that little delta t. We could have some latency in there. So we need to be very careful with our timing. And there should be a way to... Still, there should be a better system for our low speed, low velocity, low count system. And so that one is going to be called pulse period modulation. So we mentioned pulse frequency modulation. Pulse period modulation is exactly what you think. We're going to look at the length of time between pulses. And so if we have a low velocity, then we've got a really long period, so we get a lot of counts of time, a lot of counts of our clock signal, which will take us back to our high precision. And so now you can see right away that the pulse frequency modulation is better at high speed. The pulse period modulation is better at low speed. We still have the potential errors in that the stability of our clock and the latencies are going to be potentially bad. And if we've got uneven spacings, then again we've got a problem. But assuming that our clock is good, assuming that our spacing of our pulses is good, then pulse period for low velocity, pulse frequency for high velocity. And so what you could do is you could switch back and forth, or you could run them both at the same time and compare answers. And this is actually a patented, or at least it was patented, maybe off patent by now, that I haven't looked it up recently. But yeah, think about which one is appropriate. Think about whether you can use both of them. And that should give you a good high precision velocity measurement. If we want to look at position measurement, then I'm going to switch to mostly optical encoders. But if we want to do position measurement, we're going to do the same sort of thing. We're still going to have pulses, and what we're going to do is just view them a little differently. Instead of worrying about how fast they come in, we're going to count how many of them have come in. So velocity is the hard one, position is the easy one. So one type of position sensor is an incremental encoder. In this case, we've got a circular and a linear track. These two are using optical sensor, so we're using alternating transparent and opaque sections, and we've got the inner and the outer tracks and the two side-by-side tracks, and we might call these channels A and B, and then we've got an index on that linear one as well. And so what we see is that as we're looking at these, you can see that the black squares versus the white squares are 90 degrees out of phase, and that gives us what we call quadrature. It's two signals, 90 degrees out of phase, and so if you look at those, you can see right away that I can count lots of different pulses, and if I look at the order in which the pulses are coming in, it should tell me the direction. So quadrature is awesome. We can do it with something like an optical shutter where we've got a light source and a receiver, and we can either have two channels in the grate that I showed you previously, or we can do two sensors. So we've got our two receivers here, and those are 90 degrees out of phase with respect to a single grate. Either way works. And so if we make our grid size smaller than the light source, then having the two there is pretty good. But we have to make sure that they're perfectly aligned relative to the grating. So we can't just grab any old grating. We have to grab one that's designed for the particular spacing of the receivers that I've got. Now, how do we decode that? Well, if we've got our channel A and channel B, and so we've got we can read just one or the other, and we get what we call 1x decoding, and that'll tell us how far we're moving around the disk, or how far we're moving on the line. But we could also make that more precise by doing 2x decoding, where we look at the positive edges of, let's see, we've got all channel, or we could do just the rising edges in each. Either way, that's going to give us, just twice as many as just doing one rising edge in each channel, or of a single channel. We can also do 4x, where we're going to do all four edges, two rising, two falling. And so we get 4 times as many pulses, which should give us 4 times the resolution. How do we do this? Well, we're going to send this all through a hardware decoder typically, rather than doing it in software. But, whoops, there we go. There's my hardware decoder. So this is one particular one. This is an Avago brand. This just happens to be what I got some free samples of. So in this case, we've got a hardware implementation. We've got 2 channels. In our filter, we go through our decode logic. We've got our binary counter that's going to track it. And then we've got our latch with our multiplexer. But what could possibly go wrong? Well, if we do this in software, then again we've got a computation issue. If we ever lose count, then remember that there was nothing in there that tells you exactly where you are. If you lose count, you're sort of lost. And if it's binary, then the same sort of problem as before. We used gray code when we were doing asynchronous before because we wanted to make sure that we would never have data that was potentially changing. In this case, we've got data that's potentially changing, and it's changing in a straight binary sort of way. So we would want to use a valid handshake to make sure that we always read the correct data. We could also do index pulses so that we could always find some home position. But what's really nice here is that our dynamic range is potentially infinite, because our minimum detectable unit is based on the size of the grating, but the number of units that we count is based on how much memory we want to allocate, and we can allocate as much memory as we want. So our dynamic range goes way up, and if you think back analog systems, that was a problem. We had relatively limited dynamic range. Quadrature itself is gray-coded, so it's we shouldn't ever see 2 bits changing at the same time, and so we should automatically know that the A channel and the B channel, when we read them in, we're always getting good data, or if we get bad data, we can do something about it. Now the output latch is different, but the A and B channels are gray code. And this is, I mentioned no way to recover from error, but this is position information only. we only know position from this. We could differentiate it, but there are problems associated with online differentiation in terms of introducing noise. There's no way to recover from error because, again, there's typically no index. If you have an index, it's only going to be for one position. So if you lose count, you've lost your data completely, and it's very fast. This can easily be in the megahertz range, and so if you're trying to do this through software, you could run into problems. I recommend not trying to do it through software. Using an external decoder works pretty nicely. Also note that you could have A, B, and ground channels, or you could do differential signaling with A prime, B, and B prime. If you want to get really fancy with it, you could also view this as typically being more of a triangular signal rather than an actual squared off. And the reason for that, remember, is that the light is coming through, and so it's coming through this grating, and so it's going to, as the grating is moving across in front of the sensor, the amount of light should increase and then decrease. Well, if you actually want to go through this and view it as more of a sinusoid or a triangle, then you could try to read it as an analog instead of as a digital, and you could identify the position information from that. Does it work any better? I don't know. I've not actually had a reason that it was worthwhile doing it. 4x quadrature decoding is typically very good resolution as is. Certainly when you do it through analog, again, you're going to be limited by the stability of that triangle waveform and your analog noise. You could also do linear versus rotary, depending on what your case is. Rotary motion you can do with a rotary encoder, but if you're doing linear motion, your encoder then ends up being the length of your total linear motion. So maybe it would be better to use a rotary encoder with a gearing to the linear motion. It may be less expensive. It does depend on the gearing or the transmission mechanism. Which way you go kind of depends on what your application is. And from your encoder, if you want to go to velocity, you can do your pulse frequency measurement, you can do your differentiation, but you do have to understand when you're seeing a change in direction, and that's something I mentioned, that if your change in direction is relatively small, or small relative to your size of your grating, then you could end up with losing information there. So one way to do your differentiation is to do your differences in position between fixed sample times, which is just your very simple forward or backward difference approximation. But if you look into differentiation, online differentiation, it's not a great estimate. There are other ways that might be better. That's perhaps a topic for a different course. I'm going to skip interferometry. Another option you can have is what's called an absolute encoder. An absolute encoder, instead of being incremental, where you're going to measure particular counts in an absolute, you're going to say that there's going to be a whole lot of tracks, and you're going to read each one of those tracks, and it's going to essentially give you a digital value corresponding to your position. So if you look at this one, and we labeled our tracks, let's call them 1, 2, and 3 from the outside, then you notice that this whole quadrant here is going to have a value of, well, maybe I do it 0, 1, and 2. That's better. That's going to give you a value of 1. Let's see. This one here is going to be 2 to the 0 plus 2 to the 1. This one here is going to be 2 to the, oh, I miscounted that. 2 to the 0, 2 to the 2. This one is going to be 2 to the 1 plus 2 to the 4. Anyhow, you could come up with all sorts of different schemes for these, but you can see that we can count exactly where we are in each one of these. There we go. And so the absolute encoder, you always know within that pie shape section exactly where you are. Rotary works well, linear not so much. And this is a digital application, or digital alternative to what's called a resolver, and I'll get a little bit about resolvers later too. And we can do this again in Gray code we can do in natural binary, we could do in BCD. I would say gray code would be great, because if you do it in gray code, then again you know that as you're rotating through them, you should only see one thing change at a time, and so you don't have any errors. If you see two things change at a time, there's potential for errors. So that's our digital ones. The synchros and resolvers are back to analog. Synchros and resolvers are rotating transformers that will give you position, but only over one rotation. They're analog, and so what we do is we excite one of our windings, in this case winding B. We excite it with a sinusoidal signal, and then that's going to induce a voltage in winding A. And we can also put winding C 90 degrees with respect to winding A, and so if we compare the two, one's going to have a sine, one's going to have a cosine, and oops, if we have one with a sine and one with a cosine, we can extract what the rotation angle is. So a resolver is going to be a 4-wire device. We got 4 of them there. Synchro is going to be a 3-wire. So the difference being, in the synchro, we've got 3 signals. We've got our X, Y, and Z. Our X, Y, and Z are going to be 120 degrees out of phase, and then our resolver, they're going to be 90 degrees out of phase there. But in each one of these, we need to demodulate the signal. So we'll run them through something like this, where we take our shaft angle, we put it through the resolver, so we get our R cosine, R sine. Take our excitation with our PI control and our integrator to get our estimate, and the estimate will be multiplied by sine and cosine, and you can work through the math, but it does work nicely. And the PI control reduces the error in the estimate. So the output of the multiplier then, go back here, the output of these multipliers are going to be cosine phi, sine theta, sine omega t, where again this is the excitation, actual angle, and estimated angle. And so if you subtract them, you're going to get sine of theta minus phi. So we've got our error in our position, which that's our feedback loop for our PI control. And so we can then demodulate, just divide by a sine of omega t, so we get sine of theta minus phi. So if we have our PI control, this is some example here with an integrator, we can get pretty good estimations. With resolver, we can also go to digital control. In this case, same sort of thing. We've got our sine multiplier, our cosine multiplier. We've got our integrator. In this case, we're using a phase comparator with an integrator, and we'll run it through to an up-down counter, and so that'll give us our that should give us our estimate of the shaft angle, again, our phi. So somewhere between 12 and 16 bits, depending on how you do it. And it'll give you absolute angular position within one rotation. You can also do it brushless in the same way that you might do a brushless DC motor. So this will reduce your noise due to and wear due to your brush contact, because we're going brushless in this case. So that is our synchros and resolvers. That's one. Oops, I got one more slide, sorry. So synchros and resolvers versus encoders. If you look at the cost, your encoder is relatively low cost. The ones in the lab are something like $40 for the combination of the disk and the decoder. They're relatively simple, but they are limited in terms of shock resistance. I generally go with the encoders just because I think they're great. They have digital output, which I like. They're robust. And then you can do either the absolute or the incremental depending on what you want to do. And they are digital. If you want an analog one, though, your resolver, your synchro works pretty nicely. So hopefully that wasn't too confusing. We have talked about our position and velocity sensors. We're going to talk about position and velocity Actuators next. We got stepper motors, we got DC motors. So stepper motors are going to give us our position, and DC motors are going to give us our velocity, and we will pick it up there.